Hi everyone, welcome to this final lesson of the AS Chemistry crash course for this Easter edition. And remember, the goal of Easter is that you're fully confident with everything you've done in AS. So if you're year 12, you have finished all the content at this point, which means that there are final exams coming up. So you need to make sure you wrap up everything. And doing in a condensed 2 weeks can really challenge your exam application and your exam skills. That's why it's very important, even though you have a little bit of time after to revise, but at least you can consolidate on the questions that are really the most difficult for you. And for year 13 students, this is a must. So it's seriously the most important part of your exam preparation to make sure that everything you've done before, you've done in the previous years that builds really the foundation of your chemistry knowledge is confident. If you're my student, you're not going to lose marks in a year 12 question in an A-level paper, okay? No, I don't allow you that, which means that by working on the strengthening the understanding of the AES topics, building confidence with exam style questions, and learning how to avoid the common mistakes that other students have done in A-level papers, because that's what I use in these sessions, it will help you with a more focused, less stressful revision to approach the exams much more confident. Okay, so this lesson, it would be very, very important. Despite we're not going to cover every single little aspect of organic chemistry, we are going to use the techniques that really challenge your exam skills, okay? And I'm just going to reintroduce these for who has not joined before, which is we're going to think like an examiner in many questions, not all today, but a few. And we're going to mark some specific questions. So you're going to have to identify where the common mistakes are. And then, of course, you get the chance to try some exam questions. So when you see your turn, you know that is the exam questions timed, according to the number of marks available. And you can try it yourself. So make sure you have pen and paper. If you don't have that, make sure you grab it now because you're going to need to. Otherwise, again, you can write everything in the chat. But it's organic chemistry, which means that you are going to have to make some notes. Again, essentially is that whichever mistake you make, it's part of the process to make the mistakes. And this is where we really get the improvement. You're going to have to ask yourself every single time, what did I miss? What would I write differently next time? How do I have to do it differently to avoid this mistake? Okay. It's super, super important. And then, of course, if there is anything you don't understand, I'm here for that. Okay. So that's how it's going to work. We're going to mark the answer, check the examiner report, and then you're going to have to build the sensitive mark list. Okay, this is very, very important. The common mistake list. If you're already my students, you should be continuing, updating this common mistakes list, which is your own personal one, because you're going to have to avoid the mistakes that you make, in your exams. Okay. Before that, so we're going to focus on organic chemistry for all of exams, because I really wanted to focus on the general exam skills that are essential. If there is something specific for each exam board, I'm going to highlight that. So don't worry about any of this. Again, please don't stick to just one exam board preparation unless you're focusing on the exam structure and like just before the exam where you have to do like specific paper, because now it's about the general skills, exam skills and knowledge of organic chemistry. Okay. I want to really highlight how to study organic chemistry because I hope you know it by now, but if not, well, I'm just going to repeat it as many times as possible. Remember that chemistry it's not one way of studying. There is not only one method for studying because there are some topics that require understanding and some others that, well, memorization is essential. Luckily, not the whole topic is essential, isn't it? But some things like reagents and conditions, names and structure of functional groups. Unfortunately, this is only memory, isn't it? Like, how does a functional group look like? You're going to have to know that. Okay. The synthetic pathways. Yes, memory, also a bit of logic. We will see that. Definitions. Of course, definition is about memorization. But again, for memorization, you can really use different techniques like nucleophile, electrophile. If you understand a bit the meaning of the word, you would also understand the definition of what it is, and therefore you can figure it out in a mechanism, for example. So memorization, but if there are some things that require memorization, make sure you have a solid method that helps you with the memorization, mnemonics, for example, something visual. Okay. And what requires understanding? How mechanisms work. And this I will repeat it a million times, okay? Because you must understand, yeah, the essential of organic chemistry and the mechanisms. Because, like we're going to see today in some very interesting questions, in the exam, you're going to be assessed to some very specific assessment objective, no, the ones that every student fear, which is the 2 and 3, which is basically the application and interpretation. So you have to expect like quite difficult examples of things that you've never seen before. And with organic chemistry, we see it as, like most of the time. Yeah, but you need to be aware that this is a foundation of a top of a concept that you have learned. But the thing is that if you fully understand, yeah, how mechanisms and why they works in this specific way, then you can apply it to no matter what. Very, very important. The types of reaction, electrophilic addition, nucleophilic substitution, this requires understanding. We can often predict it by just doing some analysis of the molecules we have. How to determine the type of reaction from the question? Again, we need to look at the question. We can't memorize every single little thing, but we have to figure it out. And then intermediate stability mechanism, things like inductive effect, we see it we see it, for example, in alkenes. So these are very essential concepts, okay, that require understanding, which means that if you do an exercise even today and you feel like you're thinking, oh, I did this question before, all right, I did a similar question at school. No, it's not the approach that I want you to use. The approach that you have to use is always through your understanding. Because remember that memory is not reliable during the exam, but understanding it is, because your brain always finds different ways to get to an answer. Okay, so for organic chemistry, what I think is really important is that you always draw full mechanism step by steps with curly arrows, okay, but with mind, in the sense that you fully give a reason for every single arrow you draw. Yeah, no matter how many times you do the mechanism, is always with understanding, not just like writing, thinking about something else. No. Explain the mechanism aloud or teach it to someone else. Do the exam questions, by just reading reactants, predicting the mechanism before you look at the options. For example, I'm thinking about multiple choice questions that there are many of, like what is a product of this reaction, or what is an intermediate, things like that. So always be very, very visual with organic chemistry. Okay. And of course, label charges, lone pair partial charges, it's so important, because apart that are marks when you have to do mechanism is also what drives the understanding of the mechanism. Okay. So this is super, super important. Okay. And now what I want to do, it's something very like a little bit of explanations, but I think is essential, because I think organic chemistry is always taught in a way like, okay, today we do alkanes, and then we do alkenes, and then we do alcohols. But we need to understand again in a different way, because what I found in the examiner reports, but also from feedback from my students, is that it's quite, and actually something that I thought as well, like I have to memorize all of the reagents and all of the conditions, and there's so many. But again, if you understand, for example, why some reagents are used and some conditions, yeah, if you understand the meaning of it, I don't think you have to rely on memory that much anymore. So when you're asking an exam question, again, this is paper 2 for A-level chemistry and paper 3 as well, of course. When you're asked the conditions, you can now think about the logic behind it, rather than just memorizing and then, oh, I forgot that specific temperature for this specific reaction. Okay, because as we said, this is not very reliable. So this is what I would like to do now, just a few minutes of explanation. Okay. So let's understand the logic around reagents. You can often predict the correct reagent if you know the type of reaction. Okay, so let's think about like if you have electrophilic addition, think about what does that really mean? Oh, addition of an electrophile. So you're looking for an electrophile. Okay, what is an electrophile? And then your logic continues. This is what I'm trying to say in terms of, if you really don't remember the reagents, use the logic. Okay, you have other examples, but I'm going to get to more concrete, more like, solid explanations. Conditions. Conditions are important because the same reagent can give a different product depending on the condition. Okay, for example, reflux it reflux can give, as we know, reflux distillation. It's one of the bigger and one of the most important questions that come up for alcohol. Okay, temperature and solvent, of course, is also useful. And this, we know, substitution and elimination with sodium hydroxide, it's very easy to confuse because the temperature and the solvent changes. But again, we need to understand the logic behind it because, it's very important for the mechanism. Solvent. The choice of solvent influences the reaction. Why? What do we use the solvent for? To dissolve. Okay, and we're going to look in more detail at the solvent. Okay, one thing that I want to clarify is that in exams sometimes you're required to name the reaction and the mechanism. Okay, sometimes the reaction and the mechanism has the same name, but sometimes the mechanism is different. And now it's super important to have clear the difference. The types of reaction is what changes overall. And what changes overall is addition, elimination, substitution, hydrolysis, oxidation, and here is the whole list. But you really need to observe reactants and product and what has changed. Have we removed a molecule? Oh, elimination. Have we added oxygen? Oh, oxidation. Have we added hydrogen? Hydrogenation. Have we added water? Hydration. Even though the mechanism might be different, just think about hydration. It's the addition of water, like in the example of, let's look at the backward of this reaction, addition of water to form an alcohol. That's the type of reaction as kind of a general name, so what overall changes. But the mechanism is different. In fact, it's how the reaction happens. So bond breaking, bond forming. And remember, this is what we show with the curly arrows. Okay, so please don't get confused with the reaction type and mechanism. They can be the same or different things. Now, the mechanisms that you need to know, really, there are not that many. Okay, we have electrophilic addition, we have nucleophilic substitution, we have elimination, acidic or basic, nucleophilic addition, A level already, free radical substitution, and this is still AS. And then we have another one, but this would be to revise when we do benzene, which is like a whole standalone anyway. Okay, so I'm also saying this because let's say you have like, for example, this question on the left-hand side and you're like, oh, this looks so weird, I have no idea. And you have to outline a mechanism. Are you gonna figure out which mechanism? Well, you have 5 to know, okay? You can figure it out. Okay, but I'm going to help you also with other ways, of course, because as we know, to work out a mechanism, we always want to think about the nature of the substrate and the other substance that we have available, if it's nucleophile, electrophile. But we will get there to a moment. For now, I wanted to make sure it's clear the difference between the reaction type and the mechanism, why sometimes we call it oxidation and sometimes we call it with the actual mechanism. Okay. Second point that it's very important to clarify, the solvent, what to use and when. Okay, when you're asked the reagent, you should also mention a solvent. Okay, sometimes conditions, when the exam question asks for condition, they ask you for the solvent. And this is important because it would determine the type of reaction that takes place, like in the case of the sodium hydroxide I mentioned earlier. So I want to really, really clarify why we use this solvent, because I don't think sometimes this is explained at all. And it just can be confusing, but we revised this so much in the previous lessons, things like intermolecular forces, it's all down to that at the end. This is really the foundation concept for understanding the solvent, because remember that solvents, you always, and I want to look at the tip first that I wrote here, always thinks about solubility and reactivity when choosing or explaining solvent in organic reaction. And I'm sure this will change everything when you have to write, the conditions, because you can just retrieve your foundation knowledge of intermolecular forces and, the nature of the bonding of molecules and how they interact. And then you can figure out a solvent. Okay, without relying on memory again. Now, to make sure we see, like we clarify the solvents that you come across. Aqueous, are used when reagents are water soluble. For example, sodium hydroxide, right, in hydrolysis. And remember, aqueous is important because promotes ionic dissociation and effective nucleophilic attack. Why? Remember that the solvation properties of water, that water is polar, which means that it surrounds the charged particles or polar molecules. Okay, so aqueous when reagents are water soluble. Ethanolic. Why do you think sometimes we write Well, aqueous plus ethanol. Why? Don't memorize it. Think about it. Think about the substrate that you have and think about, is that soluble in water? In fact, the ethanolic or, ethanol as a solvent, even just the addition of ethanol, it's used when the reagents are not soluble in water. Okay. For example, potassium cyanide. Is that soluble in water? Maybe not that much. Okay. NH3 for nucleophilic substitution. So normally this is actually used for haloalkanes because as we know, they're not that polar, so it's not used. But very important, ethanol is called a co-solvent. In fact, what it does, it dissolves both organic structures and ionic reagents, because of course also ethanol can form hydrogen bond. But the important thing is the part that the difference between water and ethanol, just think about the bonding, no? Water, H2O, is only polar. Ethanol, it has the hydrophobic part, the CH3, and also the OH. So do you see how that can solvate both? I hope you can visualize it. If not, please message me and I will draw it out. I hope you get that though, what I'm really trying to highlight here. And then sometimes we use just water or steam, and this is specifically for hydration. And this is when water is used as as an actual reagent, and this of course normally needs a catalyst as well. Okay, I'm going to clarify everything in a bit. Dry ether. Now think about it for a moment. Dry ether, what is it? It's a solvent that basically is not polar at all. Yeah, this is used when we have very reactive metal reagents. Lithium aluminum hydrides, A-level students, you know this from reduction of carboxylic acids. Okay, Edexcel students, year-13s, Grignard reagents, because they have magnesium. So if you have a metal that is so reactive, you don't want to add it in water. Just think logically, like chemistry, it's so practical that you really need to think about like cooking, like what you're mixing together. You don't want to mix things that are explosive or they're like very exothermic, like water and like a very reactive metal like lithium, isn't it? That's why dry ether it's used. Okay. Okay, so let's take a moment to really think about all of this. Okay. Continuing, conditions. Let's clarify the conditions and why there are different ones and why different conditions are required. So always link the reaction speed, volatility of substances, or energy requirements to the chosen conditions. Because at the end, why sometimes we need room temperature, why do sometimes we need heating, why sometimes can we heat with an open flask, and why sometimes do we need reflux, and why sometimes distillation. Okay, again, it's important that you fully understand all of this. And remember, reaction speed, volatility of substances, energy requirements. So room temperature, it's used for fast spontaneous reactions when you don't need extra energy. So for example, bromine with alkenes, we know alkenes are pretty reactive, so we don't need to heat it up too much. Warm heat gently to speed up a lower reaction. For example, nucleophilic substitutions with haloalkanes and sodium hydroxide, because there is a bit less reactivity, they're less reactive, so we need to warm it up. Heat or heat under boil for reactions that need more energy, like elimination reactions. Okay, no, here it's probably a bit difficult to fully have a logic around okay, why is this more reactive than that reacted? You can really think about electron density and bond strength if that can help, because for example, an alkene has a very high electron density, isn't it? So it's going to be pretty reactive because it's going to be a nucleophile, and then of course it depends to reactive with what, for example, but that's still the logic that you can apply, because remember that at the end the whole organic chemistry is about bonds broken and bonds made, isn't it? And then think about that's why I just want you to try to use some logic for things that normally people just try to memorize. Okay, this is my goal. Heat under boil, again, reaction that need more energy, like elimination reactions. Okay, because the elimination, you're like, well, the molecule is nice and stable. Why would you want to get rid of a functional group? Do you see the feeling of, okay, maybe this needs to be needs more energy? Okay. Reflux. Reflux is prolonged the heating it's used without losing the volatile product. Okay. So if it's volatile, It means that it has a very low boiling point, which of course happens a lot with small molecules in organic chemistries, and that's why intermolecular forces is still one of the most important, knowledge that you have. Yeah? And this prevents the product loss by condensing the vapors back into the flask. Of course, we know it also for most important, and then today that we're doing AS organic for alcohols. Yeah, we know that reflux is very important. And then, of course, there are also some things that I didn't write on this slide, but I think it's important to mention that most organic compounds, they're flammable, right? Which means that you don't want to have open flames. So there is also some safety considerations. Okay. And this is for conditions. So I hope this can bring a little bit of clarity to the condition. So before I give you we talk about reagent, at the end of this lesson, I will give you access to the flashcards that I did, because at the end, okay, now, yes, we have all of this logic, but how do we study organic chemistry? Like, how can we actually remember all of this conversion? And again, remember is the wrong word, because I want you to have the logic. Okay, so really just trust in the solid knowledge that you have rather than the memory that you've built. Okay, even though you feel like, oh, but I know all organic chemistry already. Yeah, but again, maybe it's just memory. So using these flashcards, what you're going to have to do, you can really play around with with the conversions. You can recognize the structures and then predict the reaction, the reagent, the conditions, mechanism, if there is any side product that it's formed, okay? And but then before you look, it's very important, and I want to highlight this, many times, explain the logic, okay? Not just like, oh, I think this is it, okay, let me check. Because like this is not really going to work. Yeah. The learning comes from the brain effort that you put, like, oh, what is this reaction? Oh, yeah, it's this. Let me maybe picture the mechanism. Maybe you even want to write it down. And then, oh, I got the conditions right. Yeah, because I thought about, what she was saying about the reactivity or about the flammability. This is how I want you to apply the logic, because trust me, this is going to be bulletproof for the exams. Okay. And then the very last thing that I want to mention before we start exam practice is thinking about common reagents. So reagents, and you can't believe where I took these words from the mark scheme. Yeah, because the mark scheme gives a clear guidance on what is allowed and what is not allowed in organic chemistry. And we're going to look at that very soon in some practice. But remember that reagent, and here we're starting to look at the common mistakes that are done in the exam. And this is a mistake that you cannot make, because you're going to be aware of it now. Reagent is a chemical which can be taken out of a bottle or a container. Okay? This means that if you don't write down the complete reagent, you're penalized. So this is so important. When you ask the reagent, you can't say, for example, cyanide as like the cyanide ion. The reagent is potassium cyanide, because you don't take the ion out of the bottle, do you? You take it, from the whole salt. I hope you understand this point. It's so important. Tollens reagent, you don't write the ammonium silver complex ion, because again, what do you take? You take the ammonical silver nitrate, the salt. The hydroxide ion, you take sodium hydroxide. I hope you understand this is very important. And if you write both, for example, the ion and the salt, then they just ignore the ion. That's what the mark scheme asks. Okay, that says. But this is very important. So reagent, it has to be the full chemical. And then, of course, there are many common reagents. I'm not going to go through this list completely, but it's just so that you can also go back to these notes and look at this nice summary. There are a couple of things that I want to highlight, and this is something that I tell you all the time. When you think about mechanism, you must always recognize nucleophile, electrophile. How do you do? Well, you have to understand what a nucleophile and electrophile is. Nucleophile, electron pair donor. Remember, nucleophile means nucleus loving, so itself it's the negative. But again, the important definition, electron pair donor. So you find what has electron pair, or what is electron dense. Electrophile, electron pair acceptor, attract electron rich areas, okay? And here you have some examples. All of these very important, okay? Then for the others, I'm not going to mention it, because I think you can look back at this, but it's nicer to have a little summary with all of the reagents that you need to know. And then maybe you can also test your memory after to say like, oh yeah, this reagent is used for this, and that. Okay, these are always nice and dynamic ways in which you can study. Okay. The last 2 points that I want to make is Some tips on drawing organic structures. And I'm mentioning all of this because I know these are mistakes that are easy to make, because it's also maybe very easy topic for you, very easy concept that is, yeah, sure, I know how to draw organic structures. Why am I year 13 and I would be, revising how to draw displayed formula? Well, because these are the easiest thing to miss out, because we're in the exam, these are the things that we don't pay enough attention, and that's where we can risk to have destruction mistakes. Destruction mistakes are like random errors. We never know when they occur, very hard to predict, but if we're aware of them, maybe we can prevent it. So general rules, very important. If nothing is specified, you can use every rule, okay? Functional group, they have to be shown clearly and bonded correctly. Yes, it's very important. And I would always suggest you to show something more visual, like isomers must be drawn to distinguish the position. So for example, if you have an isomer and you write CH3, CH3, this could be a specific isomer, but this not. And also this means that you have to apply the knowledge of isomers yourself, right? Because you kind of demonstrate already that, you know that there are different isomers of this specific molecule, which is, bromopropane. Okay. So displayed formula, the bond angles are not very relevant, okay, which is good to know in the sense that you don't have to worry too much about thinking about the shape, but still, just for good practice, I think it's important to keep that consistent. Skeletal formula, okay, that's important that you're confident with, and I always suggest you to use the skeletal formula in a way to really sketch, things like in your paper if you're doing some drawing, okay? Common mistakes to avoid that I really want to highlight. Alcohols, okay? Alcohols is COH. Aldehyde is a CHO. This is very important to distinguish, okay? CHO is aldehyde, COH is alcohol, because otherwise you show a different functional group. Okay. And just some important things that are allowed, and it's interesting if you're not confident in writing, the formula, for example, CH3 and H3C, and notice also with the NH2 how it's written. They're both allowed, but I think it's still important to write it, always thinking about how it's connected, okay? So I hope that it's important. And yeah, one thing to clarify, this is the structure of formula, CH3, CH2, CH2Br, and I think it's very useful to use this one when you're writing chemical equations. Okay, because like this you can show specifically the atom that react, because displayed formula, the one that shows all of the bonds, that's the displayed one. But again, we don't need all of the hydrogens. Most of the time, we're only thinking about one functional group. Okay. And now, very last thing I'm going to talk so much about, I swear, and then you get practice naming. Without looking at the general rules, which you can do maybe when you revise this lesson, the tip: always break it into part, identifying the chain, functional group, number, and name of constituent. Because you think it's easy, but I know there are going to be some difficult examples. And instead that, we're going to start the exam practice.